Polynomial functions and models. The general form of a polynomial function is f of x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power. Continue that pattern all the way down to a sub 1 x plus a sub 0. So this is basically the sum of a bunch of powers of x, and what's important is that the exponents must be non-negative integers. So if they're non-negative, they must either be positive or 0. The degree of a polynomial function, since the polynomial function is the sum of a bunch of powers of x, the degree is determined from the highest power that you see on the variable, the highest power of the variable. So let's look at some examples. So first you'll be given functions and you'll be asked to determine whether those are polynomial functions from their equation. Okay, so part A. We have f of x equals the cube root of x. So we want to remember that the cube root is the same as the 1/3 power. So this is really x to the 1/3 power. Well, since 1/3 is not an integer, we know this is not a polynomial function. We know that cube root function, that's actually one of our parent functions, parent shapes we've already looked at in this class. So no, it's not a polynomial. And why? Because the exponent is not an integer. Okay, part B, g of x equals 11. Okay, so first of all, we should have recognized that this is a horizontal line, a constant function. So we don't see any power of x actually here. So if we don't see any power, we could just look at this as 11 times x to the 0 power, because we want to remember that anything to the 0 power is just 1. So if we look at it as x to the 0 power, well, 0 is a non-negative integer. So yes, this is a polynomial function, and it would be degree 0, because that's the only power of x that we have. Okay, part C, h of x equals 3 minus 5x to the 5th. So we can see we have a constant, and then we have an x to the 5th. So the highest power of the variable, the only power of the variable we see, is that 5th power. So that means yes, it's a polynomial function because 5, that exponent 5, is a non-negative integer, and the only power that we see on the variable is 5, so this is degree 5. If we look at part D, f of x equals x minus 2 over x cubed plus 4. Now, if you look closely, what should jump out at you here is that this is a rational function. Remember, rational, fractional function? So rational functions are a totally different class of functions that we'll actually study later in this course. So this is not a polynomial function. If you look closely, if you look at the numerator and the denominator separately, each of those is actually a polynomial in and of itself. But when you take the quotient of two polynomial functions, it's not a polynomial. It's a rational function. So this is no, it's not a polynomial function. It's actually a rational function. So when you think rational, think fractional. A rational function, which is actually the quotient of two polynomials. Okay, part E, g of x equals 0. So again, this is a constant function, just that 0. It actually corresponds to the x-axis. So this is a special case. When it equals 0, this is a polynomial function. We actually call this the 0 function for obvious reasons. But there's no degree, because 0 times anything would give us 0. So we could have x to the 0 power. We could have x to the first power, x squared, x cubed. How would we know what the exponent is? So there's no degree on the 0 function. And part F, h of x equals negative 6x to the fourth times x plus 2 squared. Okay, so the variables that we see, I see x to the fourth power. 4 is a non-negative integer, that's good. And here's x to the first power, that's a non-negative integer. 1 is a non-negative integer. But we can see that this is a quantity squared. So when we look at the degree, here we have a fourth degree. But if we square something in x to the first power, if we square this, we're going to get something else squared. So if you add the 4 and the x squared, add the 2 to it, you're going to get a degree 6. And to help you guys see this, if we multiply that out, so if we multiply x squared plus 4x plus 4, forgot my 4 in there, and we distribute negative 6 x to the 6th minus 24 x to the 5th minus 24 x to the 4th, you can see that the highest power in the variable would be 6. So you don't have to actually expand this out to determine that. And you're going to see a lot of polynomials in this chapter in this form, and you absolutely don't have to multiply this out. I just wanted to show you guys that for the notes. So you got your 4 here, and then if you square something to the first power, you'll get squared, so you're adding 4 plus 2 more to get the 6 for that degree 6. So this, yes, is a polynomial function because all the variables on the x, or the exponents on the variables are non-negative integers, and we have degree 6. Okay, so now when we look at the graph of polynomial functions, they're a very characteristic appearance to a graph of a polynomial function, and we've actually looked at some polynomial functions already. In our parent graphs, in our library of functions, we already know an x squared graph. We know an x cubed graph. So we know that snake shape. So you guys actually already know some polynomial functions. But if you look at these shapes, for instance, their graphs are smooth, meaning there's no sharp corners or cusps, and continuous. Continuous meaning there's no holes or gaps. And an example of a discontinuous function we've looked at is those piecewise defined functions. Those are discontinuous. Polynomial functions are continuous. So if we just sketch some examples here, here's polynomial functions. So we know these, we know the x squared, we know the x cubed. We're actually going to expand our library of functions in this chapter. But some other characteristic shapes, anything smooth and continuous like this. These would be all examples of polynomial functions. Now these would be examples of functions that are not, that we know for sure from their graph that they're not a polynomial function. So for instance, we could draw from our library of functions, we know an absolute value graph. I mean, you know that's its equation. It looks like that V shape, but because we've got this sharp turn here, this corner, that would be characteristic of the absolute value function, not a polynomial function. Again, if you draw really any piecewise looking function, that's not going to be a polynomial function. So if we sketch something like this, like the piece of a parabola, and then we have a gap, and we've got a hole here, and then we get some sharp corner here. So if this was all one function, you can see that there's a gap here, there's a hole here, there's a sharp corner here. So you've got the gap, you've got a hole, and you've got this corner here. These are all, and so on this absolute value function, we have this corner here. So we know that these are not polynomial functions. So you will be asked in your homework to look at the picture of a graph of a function and determine whether it's a polynomial function just from its shape. So you're just going to look for the smooth and continuous in order to be a polynomial function.